And we're back. In the previous video, we learned how to solve mole-to-mole stoichiometry problems. The obvious problem, though, is that when you go in the laboratory to carry out an experiment, you don't measure out your quantities of reactants and products directly in moles. In fact, you measure it out in terms of masses. So the type of problem we're going to approach in this unit looks like this. Again, every stoichiometry problem begins with a balanced chemical equation that represents the chemical reaction you're studying. In this case, we'll use the generic equation 2a plus b reacts to form 3c. And the question we ask is this. For a given mass of A, what mass of B do we need to use it all up completely? And what mass of C do we expect to get out? Or alternatively, looking at it in the other direction, if I want to end up with a certain mass of C, how many grams of A and B do I need? Well, if I give you the mass of a component in grams, can you multiply that directly by a mole ratio? No, of course not, because grams and moles don't cancel. What do you think you have to do to that mass first before you can multiply it by a mole ratio? Sure, you have to convert from mass to moles. How do we do that? Well, you know the conversion factor for converting between grams and moles is the molar mass. If you're given the mass of a component and you want to know how many moles you have, you simply divide by the molar mass. Or if you're given the moles of a component, or you calculate the moles of a component, and you want to know how many grams you have, you simply multiply by the molar mass. So a mass-to-mass stoichiometry problem really is not that much more complicated than a mole-to-mole stoichiometry problem. The only difference is you do a gram-to-mole conversion at the beginning and a mole-to-gram conversion at the end. Not so complicated. Let's take an example. Solid tetraphosphorus decoxide reacts with water to form phosphoric acid. Well, we start every stoichiometry problem by writing and balancing an equation. Tetraphosphorus decoxide must be P4O10, using prefixes, reacts with water to form phosphoric acid. I do not expect you to have memorized the formula of phosphoric acid, but I do expect you to have your nomenclature sheet with you, so you can look up and see that it has the formula H3PO4, and acid should always be written in the aqueous phase. I'll balance phosphorus by putting a 4 in front of H3PO4 to give me 4 phosphorus atoms on each side. That gives me a total of 12 hydrogen atoms on the product side, so I'll need 6 water molecules on the reactant side. That gives me 10 plus 6 is 16 oxygen atoms on the reactant side. 4 times 4, oh look, 16 oxygen atoms on the product side. Isn't that nice how that works out? So here's the type of problem we're going to see. What mass of water will I need to react completely with 10.0 grams of P4O10? And in that experiment, what mass of phosphoric acid will I get? Or another way to phrase the question is, what is the theoretical yield of phosphoric acid? You may have read this in the textbook. The theoretical yield is defined simply as the mass of product you expect to get based on your stoichiometric calculations. And then in a separate question, how many grams each of P4O10 and water would I need in order to end up with 100.0 grams of phosphoric acid? Let's start on a new page. So question A says, well, I'm starting with 10.0 grams of P4O10. How many grams of water do I need? Let's plot out how we're going to solve this problem by using what I sometimes call a roadmap. I'm starting with a given mass of P4O10. I can't multiply that directly by a mole ratio. I first have to convert it to moles of P4O10. And I'm going to do that by dividing by the molar mass. Once I have moles of P4O10, then I can figure out how many moles of water I need by multiplying by the mole ratio. The question doesn't ask, though, how many moles of water do I need? The question asks how many grams of water I need. So I simply need to convert from moles of water to mass of water by multiplying by the molar mass of water. Okay? Every stoichiometry problem has, at its heart, a mole-to-mole conversion using a mole ratio. The only difference here is that we do a gram-to-mole conversion at the beginning and a mole-to-gram conversion at the end. I'm going to set this up as a single calculation because I think that's the most efficient way to solve the problem. I'll begin by writing down the mass of P4O10 I'm given. I'll convert that to moles by dividing by its molar mass. I'm not going to go to the trouble of calculating molar masses explicitly here, just simply to save time, but I will expect you to do that in your work. So there's the first step. I've converted from grams of P4O10 to moles of P4O10. I will then simply multiply that by the mole ratio. If I flip back to the balanced equation, I'll see the mole ratio I need is 6 moles of water are required for every 1 mole of P4O10. And then finally, for the last step, I'll multiply that by the molar mass of water to give me grams, 18.02 grams per mole of water. Grams of P4O10 cancel. Moles of P4O10 cancel. Moles of water cancel. And I'm left with 3.81 grams of water. So for every 10.0 grams of P4O10 in this reaction, I need 3.81 grams of water. For part B, I'll do exactly the same process to figure out how many grams of phosphoric acid I'll get. The only difference is I'll be using a different mole ratio and a different molar mass. I'll start with, again, the mass of P4O10 that I'm given. I'll convert that to moles by dividing by its molar mass. Now, though, because I'm trying to get to moles of phosphoric acid, I'll multiply by a different mole ratio, which in this case is going to be 4 moles of phosphoric acid produced for every 1 mole of P4O10. And then I'll multiply that by the molar mass of phosphoric acid, which is 97.99 grams per mole. Grams of P4O10 cancel grams of P4O10. Moles of P4O10 cancel moles of P4O10. Moles of phosphoric acid cancel moles of phosphoric acid. And I'm left with 13.8 grams of phosphoric acid. In a problem like this, when you're calculating the masses of everything in the reaction, you can use conservation of mass to check your work, and in fact this works out very nicely. My 10 grams of P4O10 that I started with, plus the 3.81 grams of water that I calculated I need, add up exactly to the 13.8 grams of phosphoric acid that I expected to get, which is pretty cool. Let's do part C now, which says, all right, if I want to end up with 100 grams of phosphoric acid, how many grams each of P4O10 and water do I need? Again, because I'm calculating the masses of 2 different reactants, I'm going to have 2 different equations. So I'll set these up as I did before in one step. So for P4O10, I'll take my 100 grams of phosphoric acid that I intend to get, divide that by its molar mass to convert from grams to moles. I'll multiply by my mole ratio. 1 mole of P4O10 is needed for every 4 moles of phosphoric acid. And then finally, in the last step, I'll convert from moles of P4O10 to grams by multiplying by its molar mass. Grams of phosphoric acid cancel grams of phosphoric acid. Moles of phosphoric acid cancel moles of phosphoric acid. Moles of P4O10 cancel moles of P4O10. And I'm left with 72.43 grams of P4O10. I'll do exactly the same process for water. 100.0 grams of phosphoric acid that I'm aiming to get. Convert that to moles by dividing by its molar mass. Now I'll multiply by the mole ratio. 6 moles of water are needed for every 4 moles of phosphoric acid that I expect to get. And I'll convert from moles of water to grams of water by using its molar mass. Once again, Grams of phosphoric acid cancel grams, moles cancel moles, moles of water cancel moles of water, and I'm left with 27.58 grams of water. Again, because I know the masses of every component in this reaction, I can check my work by using conservation of mass. 72.43 grams of P4O10 added to 27.58 grams of water gives me very nicely 100.01 grams of phosphoric acid, which is pretty cool. So that's the basics of mass-to-mass stoichiometry.